Here's another second order homogeneous equation, constant coefficients. Y double prime plus 6y prime plus 9 equals to 0. Now, later on, it'll get a little more exciting when we start putting functions over here on the right side and they turn into non-homogeneous equations. In that case, what I'm solving for now will be known as the complementary solution. And then when we solve for the problem with that end, it becomes the particular solution. So we'll lay all that out for you pretty soon. All right, now look at this one. Y double prime plus 6y prime plus 9y equals to 0. So please fix your notes there. That should be 9y. There we go. That's better. My characteristic equation will be what? It's going to be m squared plus 6m plus 9 equals to 0. Now when we go to factor this, we find out that it's m plus 3 times m plus 3 equals to 0. And so if you solve it, you get one root that's repeated twice. m equals -3 and -3. So really there's one root, but it's repeated twice. So does that mean there's only the solution only contains one exponential term? Well, it turns out, and for the moment you have to take my word for it, that our solution is going to be y equals to c1 e to the -3x plus c2 x times e to the -3x. So there's a little bit of a complication thrown into this, that when we have a repeated root, then we still have two terms. We still have two constants, because we still have to integrate twice, in essence, to solve this problem. And so we will have two additive constants, but I can't just repeat this term over here, because then they would combine together. It turns out that I need to put an x there. And now let's see if that does work. So now this is my solution to the problem, but I'm going to check it. So if I do y prime, and I get minus, take the derivative, -3 c1 e to the -3x. And then here I've got a product rule going on, so first of all it's going to be plus c2 e to -3x, and then minus 3c2x e to -3x. And then we take the second derivative, we'll get 9 c1 e to the -3x minus 3c2 e to the -3x. And then again we have a product rule, so the derivative on x will be minus 3c2 e to -3x. And then we're going to get the derivative on either -3x part. -3 times -3 is positive 9, so we have plus 9c2x e to the -3x. I sure hope that shows up on your screen. Let me rewrite that last term here down below so it shows up a little better. Alright, that last term is plus 9 c2x e to the -3x. Alright, so it's a big mess, but I'm going to plug it into here just to verify that it works. So remember, this is what I claim is the solution to the problem. Now we're going to verify that it works. So let's plug all that in. Now here, these two terms will combine together. So I'm going to have 9c1 e to the -3x, and then these two terms will be minus 6 c2 e to the -3x, and then plus 9 c2 x e to the -3x. That's just y prime. And then we have plus 6 times this expression here. So 6 times all of this would be minus 18 c1 e to the -3x plus 6 c2 e to the -3x minus 18 c2 x e to the minus 3x. And finally we have 9 times y, 9 times this term, this expression, so plus 9 c1 e to the negative 3x plus 9 c2 x e to the minus 3x. Alright, so does that really equal to 0? At the moment I'm going to assume it equals to 0, but then we're going to just make sure. So let's look at the c1 e to the minus 3x terms. And I've got 9 here plus 9 there, that's 18. So I have 18 c1 e to the negative 3x, but here's minus 18 c1. So these two positives cancel this one negative term. Alright, that's a good sign. Here the 6's will cancel because they're c2 e to the negative 3x. Negative 6, positive 6. Those two canceled. And finally we have 9c2x e to the negative 3x. I have two of those terms, so that makes 18. And then here's minus 18, what the x is. So these two positive terms cancel this negative term. So indeed, 0 equals to 0. This is the solution. Well, that's a good sign. But the idea is that, and we're going to see this again, with the repeated roots, it turns out we'll just throw another x in there. So let me quickly give you a very fast example with 3 roots. Just to reinforce the point about repeated roots, here's a third order homogeneous differential equation with linear coefficients. Y triple prime minus 6y double prime plus 12y prime minus 8y equals to 0. The characteristic equation is m cubed minus 6m squared plus 12m minus 8 equals to 0. Now I contrived this. It turns out that this ends up factoring. It's m minus 2 to the third power equals to 0. And so there are actually 3 roots that are all repeated. Negative 2, and negative 2. So how would, can I just write out the solution to that? Well, here's how it works. Y would be c1 e to the minus 2x, and then plus c2 e x, oops, let me fix this, c2 x e to negative 2x, and then our third term is going to be plus c3 x squared e to the minus 2x. So you just keep, however many you have repeated, you just keep raising the power of x. So I'm not going to go through and verify that. You can do that if you like. It'd be pretty messy, but it'll work. And so that's the idea with repeated roots. You just repeat the exponent term, but then you start putting x's in front. So, all right, let's go on to the next one, which will have complex numbered roots.